All right, so we're going to practice and learn about Lewis electron dot structures. Often we just call them Lewis structures, but for the first time we'll say electron dot. Um, and so there's many ways in which we can represent a hydrogen atom. So if we have a hydrogen atom, and it's important to know that these are all cartoons. These are all um, not what we would consider real representations. If we were to have a microscope that could zoom in all the way to a hydrogen, we wouldn't see a solid sphere, we wouldn't see a marble, we wouldn't see any of these representations that help us conceptualize and visualize atoms. So this is just like any other. There's limitations to how we describe an atom using Lewis dot structures, but they're very helpful to make predictions, and that's why we use them. So we have a hydrogen atom. We can represent that as an H, okay, as periodic symbol. We can also represent it by our energy level diagram, okay. Or we can do in Lewis dot structure. We could represent that electron with a dot, okay. It's a form of electron bookkeeping. Okay, so the first thing is that we can think about atoms and molecules in this way, but just remember that there are limitations, and we'll talk about those. So if we have another hydrogen atom that also has an electron, those can form a chemical bond, and we can represent that chemical bond by showing electrons being shared by, so what we would say is that each hydrogen atom shares both electrons. Okay, and so that would give each hydrogen a duet, which would be 2 electrons. Okay, and so we can represent a chemical bond this way, or we could use a dashed line where the dashed line is equal to a two electrons being shared between 2 atoms. So we will use both. We will start off showing these dots, but then we'll move quickly to dashed lines and only use the dots for lone pairs, which we'll talk about next. So let's look at fluorine. So fluorine is F and has 7 valence electrons. Now we're only going to focus on valence electrons for Lewis dot structures because valence electrons are the only electrons associated with chemical bonding, and Lewis dot structures are specifically for making predictions about chemical bonding. So we have fluorine. We're going to do we're going to arrange these. Each fluorine has 7. So I know that the fluorine is going to make a bond, and so I'm going to put the electron that is going to be a part of this bond in the middle. That's 6 and then 7. So we can add these 2 fluorines together to make F2, and so we can show that F we have the 2 electrons that are part of this covalent bond, and then we're going to surround the fluorine with the 6 non-bonding pairs of electrons. So these electrons, we can either call them lone electron pairs, or short, we call them lone pair electrons, or we call them non-bonding electrons, where the electrons here are our bonding electrons. And so often what we'll do is we will show this as fluorine with a dash for the bonding electrons, and then just represent the lone pair electrons as dots. Okay. So when we are considering to make sure if the atoms have enough electrons, or if we're counting up electrons, we consider, when we're counting, we consider this fluorine to have 8 electrons, 2, 4, 6, and 8. And then we would consider this fluorine to also have 8 electrons. And so you might be thinking, hey, you can't double count those electrons. And yes, we can, because the fluorines are sharing those 2 electrons. And that's actually the whole point of bonding, is that we are getting more bang for a buck. We are allowing each fluorine to feel that attractive interaction of an electron that they didn't come with. So each fluorine feels that attraction towards this additional. That is to say that this fluorine is able to feel attraction to an additional electron that is stabilizing, and this fluorine is going to be able to feel the attraction of that electron. And so a chemical bond allows for this additional attractive interaction to occur, and so we can count those electrons double, so to speak. So each fluorine has 8 electrons, and so that gets us to the octet rule. So the octet rule is actually, there's a lot more exceptions to the octet rule than there are atoms that follow it. But the atoms that follow it pretty much make up a lot of the compounds that we'll be talking about in this class, and so it's important. The octet rule is that atoms tend to lose, gain, or share electrons to have 8 valence electrons. Now, let's make that 8 actually look like an 8. That might be helpful for later on. Now, the reason we have 8, this just comes from 2s and 6p electrons to give you 8. So in the first row, where we don't have p electrons, we actually have a little bit of exceptions. Hydrogen only needs to have 2 electrons to fill that 1s. So that's a duet. So 2 electrons, valence electrons. Beryllium is also in that first row, and we're going to see that. Well, actually, beryllium's not in the first row. It's in the second row, but we're going to see that it's going to make a quartet, or it's going to be most stable with 4 electrons. And boron is going to have a sextet, and that is going to be 6 valence electrons. Is going to do it for boron. But for carbon, nitrogen, or carbon, oxygen, or carbon, nitrogen, oxygen, and fluorine, and for those 4 atoms, we will always follow the octet rule. So second row, so what we can say here is that the octet rule, so atoms, so the second row atoms always follow the octet rule. But we find that the atoms that are further down the periodic table tend not to have, are able to have exceptions to the octet rule. They can have an extended octet, and we'll talk about why that is. And it's what we can say now. It's just because there's d orbitals, and we can throw some electrons in d orbitals, and that actually is pretty stabilizing. Elements in the second row, atoms in the second row do not have d electrons to put in. Okay, so it's also important to note that the caveats of the Lewis structure is that if we have like we've already drawn 2 fluorine atoms, we can draw these bonding electrons that are in the center, and we're going to put them right in the middle because this is a non-polar covalent bond. They should be right in the middle. But for something like HCl, we are going to find that the chlorine is going to have its 1 electron and the hydrogen electron more over towards itself, giving this partial positive for hydrogen and partial negative for chlorine. So this is a polar covalent bond. So we can show this type of bond polarity using Lewis structures. There are probably better ways to do it. Notating the partial charge on the atom can be helpful, but it's just important to know that we are not showing the actual electron localization around an atom. Even when we use things like valence shell electron pair repulsion, they help make predictions of bond angles and geometries, very well, but they are still not actually what we would see if we could zoom in and see where electrons are, because electrons um, tend not to act as particles. So that's the introduction to Lewis dot structures, and next we'll see how to what are some of the rules to writing Lewis dot structures for more complex molecules.